This question was asked in the GATE Physics paper 2020. This is a numerical answer type question having 2 marks. The topic of the question is quantum statistics. The question is, consider a gas of hydrogen atoms in the atmosphere of the Sun where the temperature is 5800 Kelvin. If a sample from this atmosphere contains 6.023 times 10 to the power 23 of hydrogen atoms in the ground state, the number of hydrogen atoms in the first excited state is approximately 8 times 10 to the power n, where n is an integer. The value of n is, so basically we have to find the integer value of n in this 8 into 10 to the power n. One information is given here, that is Boltzmann's constant value is 8.617 times 10 to the power minus 5 electron volt per Kelvin. So now let us see how can we solve this problem. It is given in the question that a gas of hydrogen atoms in the atmosphere of the Sun where the temperature is T equals to 5800 Kelvin. Now we know the energy levels of the hydrogen atom is given by E with the subscript n equals to minus 13.6 divided by n square electron volt. Here n is the principal quantum number that takes the values 1, 2 and so on. Now the ground state energy of the hydrogen atom is given by E1 equals to minus 13.6 divided by 1 square. So here the principal quantum number value will be 1 and that will give minus 13.6 electron volt. And for the first excited state, the principal quantum number value n equals to 2. So the energy of the hydrogen atom in the first excited state is given by E2 equals to minus 13.6 divided by 2 square, that is minus 3.4 electron volt. According to the Maxwell-Boltzmann distribution, the number of classical particles in an energy level E at temperature T is proportional to n as a function of, that is number of the particles as a function of energy is proportional to e to the power minus e by kBt. Here kB is the Boltzmann constant. Let n1 and n2 be the number of hydrogen atoms in the ground state and the first excited state respectively. So n1 divided by n2 will give e to the power minus e1 divided by kBt whole divided by e to the power minus e2 divided by kBt. So this will give e to the power e2 minus e1 divided by kBt. Here it is given that n1 equals to 6.023 times 10 to the power 23, n2 equals to 8 into 10 to the power n. Here we have to find this n value, and temperature is 5800 Kelvin, and we have already from the calculation, that is E2, that is the energy of the first excited state is minus 3.4 electron volt. Energy of the ground state of the hydrogen atom is minus 13.6 electron volt. So E2 minus E1 is 10.2 electron volt. Now we will find the thermal energy value at the temperature T equals to 5800 Kelvin in electron volt. So kBt equals to 1.38 times 10 to the power minus 23, that is the value of Boltzmann constant, times 5800 Kelvin, and the unit of the energy will be joule here. To convert it into the electron volt, we have to divide it by the electronic charge, that is 1.6 times 10 to the power minus 19. So this kBt value in electron volt will be 0.50025 electron volt. Now we will use the equation coming from the Maxwell-Boltzmann distribution, that is n1 by n2 equals to e to the power minus e2 minus e1 divided by kBt. So we will put the values of n1, n2, e2 minus e1 and the kBt value. So N1 is 6.023 times 10 to the power 23 divided by N2 value is 8 into 10 to the power n equals to e to the power 10.2, that is E2 minus E1 divided by kBT value in electron volt, that is 0.50025. So this will give 6.023 times 10 to the power 23 divided by 8 into 10 to the power n equals to e to the power 20.3898. Now the exponential part will give 7.16 times 10 to the power 8. From here we can write 10 to the power n equals to 6.023 times 10 to the power 23 divided by 8 into 7.16 times 10 to the power 8. So this will give approximately 10 to the power 14. So the n value will be 14 in the integer form. So we have discussed the solution for this problem and we found that the number of hydrogen atoms in the first excited state is approximately 8 times 10 to the power 14. So the n value in this question is 14.